Okay, in this video we are going to look at an example of a series RLC circuit. The circuit consists of a coil and a resistor. The coil has a resistance of 35 ohms and has an inductance of 0.133 henries. The resistor has a resistance of 45 ohms. What we want to find with this circuit is the current of the circuit, the voltage drop across the coil, voltage drop across the resistor, total power in watts, and power factor of the circuit. You can pause here and draw the triangles out that you need for this circuit. If you're a little unsure of where to start, I will show you what we use to solve these problems. Ordinarily, for series RLC circuits, we use three triangles: an impedance triangle, a voltage triangle, and a power triangle. They're always in this order: impedance followed by voltage followed by power triangles, because that is the best way to make them work in the circuit. And it's just important to know what is on each triangle. In the impedance triangle, everything is in ohms. The horizontal is the resistance of the circuit in ohms. The vertical is the reactance, inductive or capacitive, in ohms. And the total of those two is the total impedance in ohms of the circuit. The voltage triangle has every value in volts. The horizontal is the resistive voltage of the circuit. The vertical is the reactive voltage, inductive or capacitive, of the circuit. And the hypotenuse is the total voltage of the circuit. For this circuit, the total voltage in this voltage triangle should be 120 volts. The last triangle is the power triangle. On the horizontal of the power triangle, we have the true power in watts. On the vertical of the power triangle, we have the reactive power in bars. And the hypotenuse of the power triangle is the apparent power. That is in volt amps. Now, once you've seen these triangles, again, if you like, pause a moment and draw out the triangles that you would need for this circuit. Okay, with your triangles drawn out, this is what your circuit should look like. You'll have a set of triangles for the overall circuit, impedance, voltage, power, a set of triangles for the coil, a set of triangles for the resistor. This may be slightly different than how you've seen these triangles before. Sometimes the impedance, voltage, power is put down the side and the resistor, coil, circuit is put across the top. But either way, they're done very similar. So to begin solving the values for this circuit, I put down what we know to start with. The values that we know for sure, we should always start with those on these triangles and work from there. We know that for the coil, the resistance of the coil is 35 ohms. If you use the formula 2 pi FL to figure out the inductive reactance of the coil, it comes out to 50 ohms and goes on the vertical side. So we know those two sides of my coil triangle for impedance. We also know that the impedance, or the resistance of the resistor, is 45 ohms. It goes on this triangle. And one thing to note about the resistor as well is the inductive reactance of a resistor, if it's a pure resistor, there is 0 inductive reactance. So the impedance or resistance of a resistor are exactly the same value. The Z is going to be 45 ohms. And a resistor typically is just a horizontal line because there is no reactive part in a resistor, and the impedance and the total resistance are the same value on a horizontal. And so a resistor is always represented by just a straight horizontal line. Now, once we have the values on the triangle for this circuit, we work from the values we have to the values that we don't know. And where we can start here is on the coil triangle. We know the resistance and inductive reactance of that coil. And to figure out the impedance, we simply use Pythagoras' theorem, c squared equals a squared plus b squared. And the value you should get for impedance of the coil should be 61 ohms. Now, from there, we can work on our circuit impedance triangle. We typically work from the triangles we have below the circuit triangles and work upwards to our circuit triangles. Because in a series circuit, resistances add up. So we can add our values and look at this circuit impedance triangle and say that the total resistance in the circuit is the resistance of the coil added to the resistance of the resistor, 35 ohms plus 45 ohms, which would be 80 ohms, is our total resistance. The total reactive side of our circuit comes only from the coil. It's the only device that has inductive reactance. And so that 50 ohms goes right up for our X total. Now for the circuit, we know what the total resistance is and the total reactance of the circuit. To figure out the total circuit impedance or opposition to current, that's what impedance is total opposition to current. We use Pythagoras' theorem again, and the impedance will come out to 94.34 ohms, something close to that. Okay, now we know the total impedance of the circuit, and from there we can find the current of the overall circuit. And current in a series circuit is always a great thing to know because it enables us to move from one set of triangles to the next fairly easily. So the current of this circuit, I equals E total over Z total, which is 120 volts, divided by 94.34 ohms, which will give me 1.27 amps. That is the current of the circuit. Now that we know the current for the circuit, we can work to find the other values we were looking for. We know the current of the circuit now, 1.27 amps. To figure out the voltage across the coil, if we were to take a voltmeter and put it across the coil in our circuit, what would it read for voltage? To find that value, all we need to do is take the impedance of the coil times the current of the circuit. What I really should just mention here is to move from one triangle to the next when you're doing a series RLC circuit. If we have the current, we simply multiply by the current. Whatever side of this triangle you multiply by the current, you will get the same side of the voltage triangle. And to move from the voltage triangle to the power triangle, we would do the same thing again. Any side of the voltage triangle multiplied by the current would give us the same side of the power triangle. The horizontal side of the voltage triangle multiplied by current would give us the horizontal side of the power triangle. And it's the same to go backwards. If I want to go from the power triangle back to the voltage triangle, I simply divide by the current. To go from the voltage triangle back to the impedance triangle, I divide by the current. So we can go either way. We can go out using current and come back. If we were only given power values in the question, we can put those power values down here and divide by the current to go back to the voltage or impedance triangles. Okay, then to figure out the voltage drop across the coil, the impedance of the coil times the current, 61 times 1.27, will give me a voltage drop across the coil of 77.5 volts. So the voltage drop across the coil, 77.5 volts. The voltage drop across the resistor is fairly simple to do because, again, the resistor is just a straight horizontal line. The total resistance is the same as the impedance times the current will give me the voltage drop across the resistor, 45 ohms times 1.27 amps, will give me a voltage across the resistor of 57.15 volts. So now we know the voltage across the coil and the voltage across the resistor as well. The total power in watts of the circuit. For that, we want to use our power triangle. The three sides of the power triangle, of course, are apparent power is the hypotenuse, true power is the horizontal side, reactive power is the vertical side. We are looking for the true power of the circuit, or the P side, and to find that value, again, we can take, if we go back to the impedance triangle, this is the total resistance. It's on the horizontal. It relates directly to the resistive voltage of the circuit and to the true power of the circuit. I can take the total resistance of the circuit, multiply by the current to find the resistive voltage of the circuit. And I can take that value, multiply by the current again to get the true power in watts. So if I take 80 ohms times 1.27 amps, I get for a resistive voltage 101.6 ohms. Voltage resistive 101.6 volts. If I take that voltage and multiply it by the current again, I will get the total power in watts. 101.6 volts times 1.27 amps will give me 129 watts. That is the total power of the circuit. It's on the circuit power triangle. That would be the total power of it. Another way to find that value of power for that triangle as well is just to take the total resistance times the current squared. Any value from my impedance triangle multiplied by I squared will give me the total power of the circuit. So that's how you can use these triangles to find the values that we're looking for in the circuit. We have found the current of the circuit, the voltage across the coil, the voltage across the resistor, the total power in watts of the circuit, Now, all we have left is the power factor of the circuit. And power factor, I'll just move this sheet up a bit here. Power factor is always found for the circuit or for the coil or for the resistor. The power factor is always found by horizontal over hypotenuse. So power factor equals horizontal over hypotenuse. To figure it out for the circuit, I can use any of the triangles that I have. This one, I have the horizontal and hypotenuse. So if I go 80 ohms from the impedance triangle, 80 ohms over 94.34 ohms, we will get a power factor of 0.848. That is the power factor of our circuit. And that power factor is a value that we often get asked about for these circuits as well. Okay, that's the circuit. Hopefully this helps you to find those values, and hopefully it helps you to work with these types of circuits.